Okay. Here we go. There we go. All right. Good work. Okay. We are talking about planetary motion today. So we're going to talk about Kepler's 3 laws. To get to Kepler's 3 laws, though, we first need to talk about the most colorful of scientists in Physics 1. And that will be Tycho Brahe. Alright? Tycho Brahe was an excellent astronomer. He had the best telescope. He was extremely good with how precise he could follow a planet every night. Okay, so every night he would look at the stars, and he was given a castle by the king. Alright, he was given tons of money, and all he had to do was every night he charted exactly where he saw Mars and some other planets. So he had the best data compared to anyone. The problem, though, is that with all that data, he still believes that the Earth is the center of the universe. Okay? So he takes all this data and he sees these planets going around. And he's going to be so good with charting the data, he's going to see planets going around on loops. You know? And because he's so stubborn with thinking that the Earth is the center of the universe, he's going to have to draw up these really elaborate models of what the solar system must look like. Okay? Now remember, he's one of many. Most people at the time believe that the Earth is the center of the universe. You know, you have a few other scientists. Obviously, we talked about Galileo, and Galileo is going to get into a ton of trouble for saying and publishing that the Earth moves around the sun. All right, it's going to be, especially with the church. Again, the reason that the church thought that this was going to be blasphemy, that the Earth would move, was because it made sense with all their doctrines about, you know, hell being down below and heaven being up above. If all of a sudden that planet was moving, it seemed like it was going completely against the church, and everything, all their laws would be broken. Okay, so there's a big problem. There's a big controversy with saying that the Earth could move. All right, now Tycho Brahe actually did believe that some planets revolved around the sun. So I believe, like Mercury, he believed that Mercury went around the sun, but he still thought that the sun had to revolve around us. Okay, so, you know, basically Mercury was like a moon to the sun as it traveled around us. Okay? Okay. Now, think about Tycho Brahe. He's been given a lot of money. He's been given a really nice house, or a crib, if you will, for all you kids out there, yeah? Okay, anyways, he's been given really nice things, has a lot of money. He's kind of a night owl. What do you think he wants to do? Party! Tycho Brahe loves to party, okay? I don't have the slide of his t-shirt that said, "I heart to party," but just imagine that he has one, okay? Here are a few things about Tycho Brahe that, yes, you might be quizzed on. Okay? Here's one. Yes, you need to know this and write it down. Okay? Yes, really. Now, the next one, I want you to understand that this is actually very insensitive. Okay, this is something that, you know, political correctness back then wasn't the case, and we might have a student might have a brother or sister that might be a dwarf or whatever, but he essentially owned a pet dwarf named Jet. Okay, who was basically like his jester. Like I said, this is a very eccentric person. Okay, one other thing. Tycho Brahe was in a duel. And he survived, but his nose was chopped off. So he had a golden nose. So if you think about all, the people with the grills, okay, the gold teeth, they're actually all just wanting to copy a famous astronomer from back in the day. So before you had golden teeth, you had golden noses. And look, here's a picture. I'll show you the picture of his gold. It's not obviously golden, all right, but there's his nose. See his fake nose up there?
Wow.
Cool, huh? I think that's cool. There is even controversy surrounding his death. One story, one of the accounts of his death was this. Remember, he's getting paid by a king, okay? And at the time, if royalty came to visit, no one could leave the table until the royalty did. So, one story is that he had, say, the king or someone from some royalty visiting. They had a lot to eat. They had a lot to drink. Maybe a little bit more to drink. Maybe a little bit more to drink. And he had to go to the bathroom. But because the king didn't leave the table, he couldn't go. Therefore, his bladder exploded and he died of urine poisoning. I'm just saying this is one account of how he died. Okay?
Are we writing this down?
Yeah, why not? Now, what's actually more likely is this. Scientists especially didn't know anything about the poisons of mercury. Okay, and in fact, even when I was a kid, every now and then if a thermometer broke, you'd play around with it, put it in your hand, watch how mercury moved. We didn't realize how dangerous that was. Okay, now obviously if a thermometer broke in school, they'd evacuate the building. Which is why the old thermometers, we don't have the mercury thermometers anymore in schools. But what is probably more likely of how he died was that he was playing with mercury so much that he basically poisoned himself. It will make you go crazy, okay? And which might help explain why he was so eccentric. Remember also, and I don't know if we showed this video, but Isaac Newton had a big nervous breakdown. And a lot of people account that to him playing with mercury, okay? And so there was a point where Isaac Newton went crazy, had a big nervous breakdown, sent these crazy letters to his friends, and a lot of people believe that was due to mercury as well. We've heard the term Mad Hatter, right? Mad Hatter is saying crazy like someone who builds hats. The reason being is that hats back in the day would have mercury in them. And so hatters would have to work with mercury a lot. Okay? Okay. All right. Now, let's talk about Johannes Kepler. Johannes Kepler was a teacher. Probably not as good as me, but he was a teacher anyways. All right, he's actually a very, very good mathematician. Tycho Brahe and Johannes Kepler are going to kind of be like peanut butter and chocolate. Two great tastes that taste great together. The great astronomy that Brahe does with the great mathematics of Kepler will form a superpower. An excellent super scientist. The problem is they won't really get along. Okay, so Kepler goes to Brahe, okay, he's a great mathematician. He knocks on Brahe's door and says, listen, all that data that you've been collecting and getting paid for, and all that stuff to prove that the Earth is the center of the universe, well, what I want to do is I want to take all that data. So if you can just give me all that data, I'm going to prove that you're wrong. How do you think that went? Not too well, right? So Brahe obviously said, no, I'm not going to give you any of my data. But he let him stay at the castle for a little while. Come hang out, we love to party. But what happens is, Brahe dies, and Kepler steals all his data. Alright, we'll pause there, let you copy down and catch up if we need to. Pause. Alright, now, this is what Kepler does. Kepler takes all of Brahe's data after he's died, and he starts charting out. He takes all the data from Mars, and he starts plotting it out. He wants to figure out all the paths and everything for the universe. And he believes that Mars, and like all the other planets, are going to revolve in a circle. He's just trying to prove that Earth revolves around the sun. Okay, so he takes all the data and he first looks at Mars. So he plots where Mars is during its revolution. Okay? And then he draws a circle. And goes through the circle and he draws it, boom, 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 boom. And with his perfect circle, because he's an excellent mathematician, he just barely misses one of the planets. Just barely. Okay? You might have thought that, you know, maybe Brahe screwed up, but he just knew how precise Brahe was with his data. So then he moved the circle and said, all right, well, what if I try with this here? So he follows this one and draws his circle. Boom, 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 boom. And again, just barely misses a planet at one point in its orbit. So he does all these different models, tries to move things around all over. He finally realizes that planets do not revolve in perfect circles. Okay? So here is the first of Kepler's 3 laws. They follow ellipses. All planets revolve around the sun in an elliptical orbit with the sun at one of the foci, one of the focal points. Okay, we'll talk about ellipses. We're going to have a little ellipse lab to do next class. Now, again, this is exaggerated. Like I said, it's really close to a circle. And in fact, Mars is one of the more eccentric paths. Okay, Earth is very, very close to a circle. If you looked at Earth, you would think it's a circle. No planet is as exaggerated as that, as eccentric as that. Okay? And in fact, even with Mars, you'd probably assume that's a circle. But what he finally realizes is it's not. It's an ellipse. Okay? Okay. Next up. He next realized that, think about the figure skater. Remember the figure skater? When the arms go in, speeds up, arms go out, slows back down. Same thing with the planets. When the radius is smaller, when the planet is closer to the sun, it's going to go much faster. Okay? When it's further away from the sun, it's going to go slower. So you have it fast, slowing down, speeding up, going faster, slowing down. And what he realized was this. If you took a set time, let's say a month, okay, and you looked at a month, first day of the month, and got the distance from the sun, last day of the month, got the distance from the sun. Okay, then you looked at another month when it's further away. First day, got that distance. Last day, got that distance. Obviously, when it was close to the sun, it was going faster, so it would have a longer distance here. Slower here, so it's going to be shorter. But it's further away here, it's closer there. What he actually figured out was that the area would always be equal if the time was equal. Okay? Now obviously one is shorter and wider, one's longer and skinnier, but the area would always have to add up to the same amount if you have a set time. Okay? Now again, don't get confused. Remember, this isn't the seasons. This isn't summer and that's not winter. Right? That has to do with the tilt of the sun, or the tilt of the earth. But this is the idea, is that when it's going faster, okay, it's going to be closer, but still the areas will always be equal with a set amount of time. Okay? Alright, last one is this. He looked at all the planets he had data for and figured out the time it took to go around the sun and the average distance from the sun. So T would be the period, R the radius, orbital radius. Okay? And he looked at those ratios. And if he just did T over R, you really didn't get anything. They kind of changed a little bit. After using all the data, he finally realized that if you squared the time it took to go around the sun for that planet, let's say Mars, and you cubed the average distance from the sun for Mars, you get some kind of ratio. If you did that for any other planet, you would always get the same value. Okay, so what I'm saying is, you know, not that the ratio, not that 1 over 2, you know, not that 1 is equal to 2, but 1 over 2 is equal to 2 over 4. Obviously it's squared and cubes, but every time you took a value for any planet, squared the period, the time it took to go around the sun, cubed the radius, the distance, average distance from the sun, it would always give you the same exact constant, k. Okay? Now think about how that's useful. Pluto takes 247.7 years to go around the sun. It's not like somebody can say, hey, I discovered Pluto, and I'm going to wait for it to go back to that same spot. Right? So what happens is every time you find something new in the solar system, if you can figure out how far away it is from the sun, you can then work your way back to figure out how long it takes for that planet to go around the sun. Okay, or vice versa. If you were able to figure out time, then you can work your way back and figure out average distance. So this will be used by all the other astronomers to start plotting and mapping out where other planets are in our solar system. Okay? Now, I want you to remember something, though, about this. How hard it was. Remember that we're moving. Right? So it'd be one thing if we're like looking on the outside, we're over here, and we see the sun, and we see the planet moving around, and using that data. But we are moving, and we're inside. So we're going along, okay? We're moving all along here, and while we're moving around the sun, we're following other planets moving around. That's pretty hard to figure out and map out. So this was no small task to figure out where the other planets were and follow their paths while we're actually moving as well. Okay? Alright. Well, I'll let you copy that down. We'll pause for station identification. Alright. The way you draw an ellipse is if you have two foci. Here's my foci. 2 push pins. Alright? And you have a set distance with a string. To draw an ellipse, all you do is trace. Okay, that's what an ellipse is. Alright? Now, the further away the foci are, the more eccentric. Okay, you ever hear the term, that guy, the rich eccentric guy down the street? He's a little bit off-center. You know what we're talking about? Right, when you hear about that eccentric guy? Off-center is the same with this. Eccentric meaning the foci get further and further away from the center. Okay? The more eccentric, the further away the foci are from the center, the more elongated the path. Okay? So that's how ellipses are made. Alright, what happens if you had 2 push pins that are basically on top of each other? What if the foci were directly on top of each other? It would be a perfect circle. So the eccentricity, in this case, would be 0, and therefore you'd have a perfect circle. Okay? You're going to do a lab making ellipses. Alright, now to figure out and calculate the actual eccentricity, though, all we do is we get the distance between the foci. Okay, so I'd measure the distance between the push pins, and measure the distance, the longest distance you can measure in that ellipse. Okay, mathematically they call that the major axis. Okay, so if you wanted to measure this, and then measure that and divide them, you would get your eccentricity. Okay, like I said, Earth's is very, very small. Earth's eccentricity is 0.017. Alright? Halley's Comet is 0.97. So Halley's Comet is extremely elongated, which is why Halley's comets will go to the outer edges of the universe, okay, or not universe, sorry, solar system. It's going to go all the way past all the planets and outside their orbit, and then come back in, which is why it takes whatever 78 years or whatever it is to come back near Earth again, because it's a very eccentric orbital path. Okay? And again, like I said, if eccentricity was 0, if they were one on top of the other with a foci, you'd have a perfect circle. Alright. Now, real quick, I just want you to understand aphelion and perihelion. Perihelion is when the planet is closest to the sun, right? Helios means sun. So perihelion is when it's the shortest distance to the sun. And to figure out the perihelion, how would you figure out this distance here? Any ideas? In terms of C and A. Subtract them and you get this distance, and then what would you do? You'd have this distance and this distance.
Divide them by 2.
Divide them by 2. So the perihelion would be the major axis minus the distance between foci. And you get these distances left, divide by 2. And that's how you get perihelion. Alright? To get aphelion, you'd get that perihelion distance and add to it the distance between foci. Okay? Okay. End it there. Thank you.